they're still solid, but different types of different solid with a different shape there. Okay, but the total volume will stay fixed. Liquid volume is fixed. If you have 500 milliliter water, whether you put it in a small bottle or a large bottle, the volume stays at 500 milliliters. Okay, so volume is definitive, but the shape depends on the container. You put it in a round container, and the shape is wrong. If you put it in a square container, it will take up the square shape there. The gas, something that we will be looking into in this particular chapter. The volume and the shape all depends on the container, the size of the container. If you have a 500 milliliter container versus a 50 milliliter container, you can put the same amount of gas in either of the two containers there. So the volume obviously is different, and the shape and also can be different there. So the gas property and the volume of the shape of the gas depends on how and where you put it. You can put two single molecules of oxygen gas in this room, and then we would say this room, the entire volume of this entire room would be the volume of those two oxygen molecules. Okay. And you can put it into a very tiny container there, and the total volume of those two oxygen molecules, that's the volume of those two molecules there. So volume and shape of gas depends on the container there. And there are some properties that we try to generalize, and we call it general properties of gases there. So this is something that we want to review together. Talking about the general properties of gases there, the assumption there is that gases are composed of a large collection of particles, molecules, gas molecules there. And those particles are always in random constant motion. Okay, so they're not standing still, they're moving around. And they're colliding with one another, they're colliding with the walls of the container. So that's the first assumption there. Okay, and then also, when you have a container, when you put a certain amount of gas in there, it doesn't matter how much, and the gas will occupy the container uniformly and completely. Okay, so whether you have 2 molecules of oxygen gas in this room, or you have 2,000 molecules of oxygen gas there, well, we would say, once you put the molecules in this room here, well, the entire volume is occupied by the gas molecule. So, and they will occupy the container uniformly and completely. And gases also diffuse rapidly to form a homogeneous mixture. That's why when you bring a freshly baked pizza, food again, in this room there, when you open the box there, and within 5 minutes there, the whole room will smell like pizza. The gas molecules are diffusing and trying to form a homogeneous mixture. Okay, and also most of the volume of the gas will be empty. The example that I use there, if you put 2 molecules of oxygen gas in this room there, we would say the entire room, the volume of the entire room is the volume of the gas there. Well, the molecules are extremely small. If they occupy such a big volume, then most of the volume is empty space. There are only 2 very tiny particles occupying the entire space there. Most of the volume would be empty space. Okay, so these are the assumptions that we make about in terms of the general properties of gases there. And keep these in mind when we study the property of gas. Because when you change the pressure, when you change the volume, when you change the temperature there, things will change. The behavior of the gases will change. So when dealing with gases there, we also make these assumptions, well, based on the general properties that we summarized on the previous slides there. Gases consist of small particles. We treat gas molecules as little particles. Okay, and we will take one step further. When we look at them as small particles, we assume they are hard spheres, okay, and the solid hard spheres. And they have mass, but they do not occupy volume. That's an assumption that you know. Volume of the particle of the gases there, gas molecules there, no matter how small, they would take up certain amount of volume. But since the distance between the gas molecules under normal condition is pretty big compared to the size of the molecules there, we can neglect the volume that's taken up by that small particle there. Okay, so it's not on here there, and this is what we call kinetic molecular theory. We make these assumptions to make the study of the gas behavior a little bit easier, because each gas is different. However, they do share some commonality there. So we assume gases, all gases consist of small particles there. And gas particles are in constant random motion, and they do not lose energy when they collide with one another, when they collide with the wall of the container there. And the average kinetic energy, and that's something that's that we will look at again in the sixth learning objective number 6 there. We won't look at this term again. And the average kinetic energy of the gas particle is proportional to the temperature of the gas. Okay, so the higher the temperature, the higher the kinetic energy. Now, we haven't talked about the energy part of the chemical processes yet, and that's the topic in the next chapter there. But for now, we just want you to remember kinetic energy, EK, equals to 1/2 of mv squared. M would be the mass, and V would be the velocity. This is an equation that you will see in the physics class there when you talk about kinetic energy of a moving object. It has something to do with the mass. It has something to do with how fast they're moving. So we say here the average kinetic energy of a gas particle is proportional to the temperature. So this quantity has something to do with the temperature. The higher the temperature, the faster the gas molecules will move. And the faster they move, the higher the amount of kinetic energy. Okay, so these assumptions are known as the kinetic molecular theory, and this is something that we will look at in the 4th learning objective in this particular chapter there. So with that, we want to take it one step further, and when we deal with gases there, we know we have carbon dioxide, oxygen, hydrogen gas, and different types of gases there. Now, how do we come up with a universal equation or a gas law so that we can use that to study the behavior of the gases there? Well, we make some assumptions there, and gases are different in terms of their molar mass, in terms of their chemical properties and all that. Okay. Now, when you study gases there, we can actually make some generalization there, and then assuming all molecules of gas are considered to be small hot spheres with mass, but their volume is negligible, because under the condition, normal condition there, room temperature 1 atm, the pressure, the air pressure here, and we consider the particles and the distance between the particles of gases are much, much larger than the size of the particle. So whatever volume that each particle occupies is negligible. So all collisions between gas molecules, and the second assumption there, all collisions of gas molecules are total elastic, meaning if they bounce into one another, they simply bounce back to the opposite direction with the same speed, moving to the opposite direction there. Okay? So there is no energy loss. Like when you have two cars bump into one another, well, some of the energy is being used to de-shape the car. You see the bumper crumples and all that. Okay? And we assume when gas molecules collide with one another, and there's no loss of energy. Okay? So energy are simply exchanged between the particles of the collision, in the collision there. And all of the motions are frictionless. Okay? These assumptions basically tells you there's no energy loss in collision or in motion. Okay? Now, this assumption is valid under normal condition. Again, the normal condition that we define, room temperature, low temperature, relatively high temperature, comparing to in physics and chemistry there, room temperature is considered a high temperature there, and low pressure, 1 atm, somewhere around the normal condition there. Okay. And then the Newton's law, since they're small hot spheres, Newton's law applies, F equal to ma. If you push if you apply a force on a gas particle, then the particle will accelerate.